So in the last two classes, we have introduced ourselves to CUDA. We've seen how to um, launch our CUDA kernel using the threads and the blocks, and how the thread block calculation is done, how it is mapped onto GPU into WOPs, and how the CUDA kernel executes. Now, in this class, we will learn more about CUDA in terms of how memory is used in CUDA, what types of memories are available to you, and how they are utilized. I know that you were, according to your handout, you were asked to only have two classes on CUDA. But from what my understanding is and what I have learned, it is not possible to cover CUDA in just two classes. We will need to learn more about it, and to learn the implementation of CUDA, you have to learn about all the aspects, including the launch configuration as well as how the memory is organized. It's a very critical part of designing CUDA solutions. So in the morning class as well as the evening one, we will try to complete CUDA in these two classes and then move on to the next topic, the final one. So let's begin. So how the resource is partitioned in CUDA, or how it is decided how many threads can be on a particular SM. I hope you all recollect what a SM is. If not, let me just revise. So our GPU architecture has multiple SMs, right? SM is a streaming multiprocessor. So each SM then has a certain number of ports, a certain number of special function units, load store unit. It will also have tensor cores and so on. So now when our thread blocks, this is, let's say, SM0, this is SM1, and this is SM2. So usually they are more than 10 in most of the current GPU architectures. So now when we try to assign these thread blocks that we launch to these SMs, what we do is the block 0 will get launched here, block 1 will get launched here, block 2 will get launched here. In the next cycle, B3 will get launched here, B4 will get launched here, and B5 will be launched here. Now, at the point, how many blocks will reside on SM will depend on the hardware, constraints that it has. So the maximum threads which are allowed to be on a SM at a time is around 2048 for most of the NVIDIA GPU architecture. You can get this data using the device query. So when 2048 threads are the maximum allowed on SM, it need not be the case that every time 2048 threads might reside. And why is it so? Is because we also have to consider for that particular thread of that block, what is its requirement in terms of resources. What resources I'm talking about is registers per SM and shared memory per SM. So how many registers per thread we need, depending on that, and what is the architecture's availability. Like Kepler has 64K registers and Fermi has 32K registers. So if we have more threads with fewer registers, then we can have more threads on the SM. But if we need more registers, then fewer threads can reside on one SM at a time. Similarly, based on shared memory requirement, we can have more blocks if the shared memory requirement is less. But if the shared memory requirement is more, we can only fit a fewer blocks on an SM. Okay. and that's how the resource is partitioned. So hence, when you are trying to, if you want to fit a lot of blocks, a lot of threads, these two requirement of these two, that is the registers and shared memory per block, will have to be lower. Only then you can fit more number of blocks or more number of threads. So these are like the technical specifications of compute capability from 2.0 to 3.5. Anyone can recollect what compute capability is? I think we had a discussion on this last class. You know, it has been a longer break this time. Anyone can recollect what is compute capability?
Processing power. Processing power. Considering number of cores, blocks and all.
Okay, you are not completely wrong, because compute capability deals with the architecture.
Yeah.
So NVIDIA introduces almost after 1.5 years a new architecture, almost most cases. So every architecture is given a number which is its compute capability. Now this is Kepler. This is Fermi. The current compute capability, I think, is around about 9, because after Kepler came Maxwell, which had around 4. Then there was Pascal architecture, which had around 5, 6. Then
Hopper also.
Yeah, Hopper is the new one. So
new one.
Then there was Volta, then there was Turing, then Ampere. Now we have Ada Lovelace. So every new architecture, when it is introduced, it is given a compute capability. So this number tells what are the, let's say, features like maximum threads that can be per block, then how many concurrent blocks can exist, then how many number of 32-bit registers are available to you, how many maximum number of threads you can have, what is the maximum amount of shared memory per processor that you have, or per SM basically you have. All these features, apart from how many cores can be there, how many SMs can be there, all this thing is related to its compute capability.
I have a question. Maybe it's not directly linked to this, but I have one thing.
That's fine.
Recently, it's like you know that the market NVIDIA GPUs are being so much popular for the AI inferencing.
Yes.
Right.
Yes.
So now these systems are being called in the HPC systems. Correct. But for a real HPC system, they actually work on MIMD taxonomy, right? That architecture is MIMD, multi-instruction, multi-data. But this GPUs are actually SIMD, right? Single instruction, multiple data with the multi-threading, right? GPUs are actually multi-threaded system, the processor. Yes. So why we call them as an HPC? The real HPC means supercomputing, right? So high performance computing. So they actually means supercomputing means when they process multiple instruction on multiple data answer, like if they follow that. So why we are calling them as an HPC? Is there any generically we are using the term because they are so much powerful, capable of doing the parallel processing, or there is any real technical reason?
See, HPC, as you correctly said, is supercomputing, right? Or using parallel processing to solve some computational problem, right? Now, this HPC will have multiple nodes, right? It could be a cluster, or it could be part of data center. Now, in these multiple nodes, you will have these multiple nodes will have multiple GPUs. So you can say that a MIMD architecture may have will be a multiple computers connected over a network, right? And these multiple CPUs that have will might share some resources and will also have multiple GPUs which are connected together.
Yes, agreed. It is a distributed system. Still, it is distributed because definitely GPU single system is not running all this. But the base idea is same, right? Even though it is a distributed system, the multiple system all together sharing data over NVLink, NV switch, and all what the fastest Ethernet. And then, but idea is that they are still processing the same instruction, not the multiple instruction, even though they all together working on that thing.
May not be the case. Same, it may not be the case. Since there are multiple nodes involved, some nodes might be doing, let's say, some physics simulation. Some other nodes may be doing some chemistry simulation. Some other must be working on some, some kind of dense linear algebra problem or an ML problem. So all these multiple nodes of your HPC or a supercomputer which feature GPU may be working on different tasks.
Yes, it is case in the HPC, real HPC system, but I'm referring to this particular NVIDIA systems, which let's take an example. Like there are a bunch of multiple systems with views, and they are actually working on some LLM. They are there is an LLM model, and then they are processing the large amount of data set, and then they are trying to create an the data model is model learning and all this stuff is going on. So in particular in this case, like Gen AI case, LLM and all, so they are actually addressing one single problem only, not the multiple problem.
So now that's what I'm saying. It depends on what is the problem. Like LLM, if you are training LLM or if you're running LLM, maybe the whole HPC system is being used only for LLM. But let's say HPC cluster is a cluster which is in the university, like in most universities, big universities have. Okay, there are schedulers which are scheduling different jobs which are submitted by different professors and scientists or PhD scholars. Depending on the resource availability, they'll schedule the job. So it may not be the case that only one job is being done there.
Okay. Thank you, ma'am.
Does that answer your query, or?
I'm still little confused, but I don't want to waste their time here. I will.
So I understand, but even I did not understand exactly what. Can you please repeat once, or maybe then we will move on.
So my question was like, ideal HPC supercomputing system, they work on MIMD architecture. They process multiple instruction at a time, along with the instruction operating on the multiple data. Correct? That is what it is. Now, in case of NVIDIA GPUs, they are the SIMD. So there will be only single instruction. Definitely, they will be processing multiple data at a time, like vectors, all right, like large matrix vectors and all. So idea is that they are SIMD system. Why do we call them HPC? Even though I understand the taking example of again the LLM data, large amount of data processing and all. So the instruction is still same, but definitely they are operating multiple thousands or millions of data sets, right? That's where GPU demand is used into, especially in the AI inferencing and data modeling and all. So in today's, why we call them as a multiple, HPC? Why is there any technical reason?
Okay, your question is very, very relevant to what we are discussing, in the sense that, as I mentioned, we can fit on an SM the number of blocks based on what is the requirement of the block. Okay. So what if your GPU code, your CUDA code has multiple kernels? Okay. Now these multiple kernels can also execute simultaneously on the GPU. It's not that every time only one kernel is scheduled.
Yes,
So
yes.
if you're,
I mean,
if
see,
you're okay, if two of these kernels are running parallelly on the GPU, that means it also becomes MIMD because it is not only single instruction, because some part of it is running multiple instructions, because different kind of instructions on two different parts.
but ideal architecture for NVIDIA is like what we read is SIMD, right?
It is SIMD. It is SIMD for a particular kernel. It is because if one particular kernel is running, then for that particular kernel, when we divide these threads into warps, each warp of 32 threads will get the same instruction in every cycle.
Okay, what you are saying is maybe system architecture is SIMD, but at a time parallelly when we
Yes.
add multiple instructions, in that case they will be acting as an MIM,
Yes.
right?
Yes.
Okay.
Yes. Yes.
Oh, okay, fine.
And this is also not traditionally the someone is, I think, unmuted. May I know? Okay. So yes. So
Yeah.
yeah. Coming back to the point. Yes. So when the GPUs were designed first, they were not MIMD. Only one kernel could execute at a time. But now with the capability that newer capabilities that were added, like streaming, uh, hyper queuing, with all those, it has the scope to be SMD as well as MIMD at the same time.
Okay. Okay. Now I think now it's clear. Yeah. Thank you, ma'am.
Yes. Okay. Continuing our discussion. So this is how, based on what is the resource that is used, that is the registers or shared memory per SM, we can fit as many threads that are available based on the resource and the maximum capability of your architecture. From where you can get this data is based on the compute capability or based on the architecture. You can either refer to the white paper, which is published by NVIDIA for each of the architecture, which provides all these details in detail. Also, there is a code which is a device query which is available for you in CUDA samples. When you execute this device query, you get all the details of your machine that you are running on, and it provides all these details of how many maximum number of threads you can have per block, what can exist per SM at a time, and all those, and much more. Now, how CUDA or NVIDIA also provides something called as a CUDA GPU occupancy calculator. So with this calculator, you can calculate what is the occupancy of your GPU, or what is the amount of, or what is the number of threads that are active at a time on your GPU. So how that is decided, how the resource is partitioned, is what you need to enter is what is your thread per block, how many registers per thread are being used, and what is the shared memory per block. You can get all these details. This you can get by going through your code. These two things you can get at compile time using a NVCC flag. So you can get all three details once you enter these details, and also choose the compute capability of which architecture you are trying to calculate for. This provides you what is the occupancy of each SM. From occupancy, you can analyze how many number of threads are active per second. It also provides you many more things as well. And it's a just Excel sheet, so you can go ahead and download and go through it. So there are the choosing how many threads you should have per block. There is no fixed rule as such, or no best approach to it. But there are a few guidelines which might help. One of them is always keep the number of threads per block to be a multiple of warp size, that is 32. So it could be 32, 64, 128. And why is that? Because eventually when they will execute in terms of warp. And since they are already in the size of 32, they will get they will, the instructions will get divided or will be launched for this particular warp, and the execution will happen smoothly. If it is odd, then you might have to you know launch a extra warp which could be have only half of the threads. It is not efficient in terms of performance. You should avoid small block sizes, that at least 128 or 256 threads per block is ideal. Why it is so? It's because if you have 128 or 256, you get better occupancy. That is, more number of threads are available to you per cycle on an SM. You can confirm this using experiments, or you can even verify this using CUDA occupancy calculator. So then you can adjust the block size up or down based on what is the requirement of your kernel. That is your threads, your register requirement and shared memory requirement. Also, the number of blocks should be much greater than the number of SMs. Why? Because as I mentioned, you start allocating each block to each one SM. So if you want all the SMs to be occupied at a time, then it is better to at least have your number of blocks to be greater than your SM so that they all get occupied. And last but very important thing is, do not settle down with one thread, one configuration. Keep experimenting. Change the configuration, maybe increase the block size, or decrease the number of blocks. Try things out, and with that only you can get what is the best execution configuration or the best performance that you can achieve with your code. So these are some of the results on Tesla M2070. So what do you think about these results? So here in this result, you can see that the sum matrix, if you launch using 512 blocks or 512 threads, sorry, these are the number of blocks, these are the number. So 512 cross 512 into 32 into 32, the time taken was 60 milliseconds. If you decrease the number of threads and increase the number of blocks, the time became 38 milliseconds. If you further decrease the, if you change, just change how this block configuration, made it ulta, the time increased again. If you reduced the number of threads further, this did not give you a better result than this, but in this particular experiment, this seemed to be doing much better. So slowest performance is for 32 by 32, and the fastest is 32,16. So we cannot say reduce the number of blocks significantly and that will improve your performance, or we cannot say increase the number of blocks and that will help. So you have to keep experimenting and finding out what works best for your application. Or another way is go and profile your code. Now the one of the NVIDIA profiler was NVProf, which is now replaced by Insight Compute and Insight Systems, which we will learn maybe in the evening. But the previous profiler, which was NVProf, was also very well built, and you could profile a lot of metrics using this NVProf. So here, if you check your occupancy of your kernel by using the metrics achieved occupancy, you can see that in this particular case, the highest occupancy is for 16 by 16. So can you say that one with the highest occupancy is doing the best? It's not the case, right? Here, although the occupancy is lower than this particular configuration is executing and giving you the best performance. So hence, we cannot only say that it depends on how many threads are active at a time or how many threads are occupied or at a time that will define the performance of your code. You can further, profile it for other metrics. So here, what we have done is we have profiled, okay, we have also changed this and run this for this blocks configuration. And we found out this takes 32 milliseconds and this takes 30 milliseconds. So that means 256 by 1 is the best block configuration for this particular example of submetrics. So this is the best configuration. Let us now profile it further. I hope what is profiling you all know. Profiling is rerunning the code multiple times by a tool and collecting data of execution of this application and then presenting to the developer so that he can analyze what happened during the execution. All the metrics that are important for execution can be shown, and also what are the bottlenecks in your code. How can you fix your code so that you can get better performance? All these things you can learn by profiling. And NVIDIA provides really good profiling tools to you.
Ma'am, I do have a
Yeah.
question here.
What?
For every program, we are passing two numbers. Like those are the threads number, or what is that number?
So these, so this 32,32, as you can see, are taken as argument and are assigned to block configuration, right? When you launch a kernel, these are number of blocks. Yeah.
Is it dimension of the matrix or what is this?
No, this is number of blocks and number of threads per block.
And what is the second one?
This is threads per block.
Okay, and these are the first argument is number of blocks.
Number of blocks, yes.
So we are running on two blocks, and each block having 32 threads.
No. 512 cross 500.
Okay, it's the dimension of the block.
Yes. So 512 cross 500 is it the value?
And this 32 by 32 is each inside each block. Again,
those many threads are there.
Okay, 32 by 32.
Yeah, so this is 262.
Okay.
144 blocks are being launched.
Mm-hmm.
And 32 cross 32 threads. So 32 cross 32 is 1024. You cannot do more than 1024.
Mm-hmm.
You cannot have more than 1024 blocks in a thread because the maximum number of threads per block can be 0.024.
So,
Okay.
ma'am, one question here. So,
Yeah.
when from programmer's perspective,
Huh.
when he's coding all this, right?
Yeah.
How do he know that? Okay, at the time when he's coding all this program, how
Yeah.
would he know that on which architecture of this code will run ideally? At which physical architecture will run? Because there are per architecture wise, if I'm understanding correctly, there are limitation of number of cores and all, right?
Yeah. Yeah.
So
So,
how would he decide that?
third, so he can first of all run NVIDIA SMI, which is uh, NVIDIA's command, which provides you details of what GPU you are executing. So,
Okay,
uh,
that is in
then
his own let's say
machine.
development environment. Yeah, development environment he is running. But
Yes.
so in that case, are we not limiting the capability, the scaling of the program? Let's say I might have lower version on my system or development system, but on the production it might be the bigger, higher architecture. I might be using it. So if I am because I am coding as per the development environment, let's say old architecture which has less number of cores, but on the production it is a higher number. But because I have tested on the lower system, so somehow I have already limited my system. So is there any way where dynamically these can be assignment can be done based on the architecture?
So that's what. Now here you have 512 to 512, right? So this value comes to around 262144. Okay. Now, when you execute this code on an architecture which has 13 SMs, at a time, out of these many blocks, 13 blocks will get assigned in the first cycle. Next cycle, another 30. If the same code is run on a GPU which has 64 SMs, in one cycle, 64 blocks will get assigned. So scaling is inbuilt in the way the CUDA program is designed. Is it clear? So based on the same code, another thing that you can do is you can also compile, when you're compiling a code on a particular architecture, you can mention the architecture by providing -arc after your NVCC. If it is 3.5, here you have to provide the compute capability. When you do that, NVCC automatically optimizes your code for that particular architecture. That feature also is available in your CUDA. Is it clear how the CUDA has built-in scalability? Because based on what are so that's why you should have more number of blocks.
Mm-hmm.
Because wherever you run your code, it will start assigning the one block to one asset and keep adding more depending on what is the resource available on your machine.
Understood. Yeah.
So now moving on. Okay, so when we now profile this with other metrics such as achieved occupancy, global load throughput, global load efficiency. We saw that in this case, the achieved occupancy was good, the load throughput is good, and load efficiency is 100%. Possibly for this particular execution, because of the best global memory load efficiency, we got the, sorry, not this, my bad, this. We got 30 millisecond performance, right? We got the best performance. Possibly that's the reason. May not be always the reason. That's why in most cases, no single metric will work and say that you do this and you'll get optimal performance. Which metric or event most directly relates to overall performance depends on what is the code of your what is the application. If your application is memory bound, maybe there the load efficiency will have a higher contribution towards a better performance. If your code is more compute bound, that time that time maybe the number of blocks or the occupancy will have a higher weightage. So you better have a balance among all these related metrics and events, and profile your kernel. Check the kernel from different angles and find this balance amongst whatever related metrics are there. Best to start, you should always try out different grid and block heuristics and see how it affects the performance as well. And then move on to profiling. Understand among these different grid and block heuristics, what are the different important metrics, and then choose the best one that works for you. Okay, moving on. We will discuss the CUDA memory model. We'll start with a few types of memory and then maybe take a break and then continue. So, why CUDA memory model needs to be studied separately or should be given its due? It is quite, you can say, complex. At the same time, very well explored or designed, and is created in such a way that it can take care of multiple needs of applications that can run on GPU. Since traditionally GPUs were meant for graphic processing, there are still memories assigned only for graphic processing, which are also sometimes used for general purpose as well. So, as you can see in this figure, these orange are different types of memories you have. You have registers, you have local memory, you have shared memory. As you can see, registers and local memory is accessible only by the thread. Different threads in a block, inside a block, can access shared memory. Multiple threads in multiple blocks can access global, constant, and texture memory. Global, constant, and texture memory is also connected with your host memory, that is your CPU, and you can move your data from your CPU to these memories and then can be used. So let us discuss each type of memory in detail. Registers, like CPU, in GPU also, they are the fastest memory space. And they are also partitioned among active blocks which are available on your SM at a time. These are private to your thread. We also saw the resource, how the resource partition happens. If kernel has more registers, access registers will be taken over from the local memory. If you need more registers, it will be taken over from local memory if they are not sufficient. This is known as register spilling. But this also affects that in a such a way that since thread uses more of local memory and it does not for registers and does not have enough, it might have an adverse effect on performance as well. So NVCC tries to use this, understands and uses these heuristics and avoids this spinning as well. Then you have local memory. Local memory is where you have variables in your kernel that are eligible for registers but cannot fit into the allocated register space, will come into your local memory. It could be some local arrays, large local structures, or any variable which cannot fit in the kernel register. These values, although are in local memory, they are part of the global memory. They are physically on your global memory. Then you have shared memory. Shared memory is on the SM. It is high bandwidth and low latency. That means you get the data very fast from your shared memory and in a very low amount of time. We had discussed this in the last class, I believe. The latency of your shared memory is around 30 cycles, whereas your global memory can be around 800 cycles. So this is almost at least it is 10 times less slower, then faster than your global memory. But you cannot use global shared memory for everything. Just because it's faster, you cannot use it for everything. Reason is SM has limited amount of shared memory. So although it's fastest, it is limited. So you have to use it efficiently and you need global memory. You cannot say that I'll only use shared memory. You cannot fit all the data on shared memory. You have to keep the data on global memory, fetch only what is required to be processed, bring it to global shared memory, do the computation, then maybe move back the data to global memory. But each type of these memories have its place and reason to be and have to be used accordingly. Shared memory is active only during the lifetime with the thread block. The thread block which is using it only during its lifetime, whatever you put in the shared memory will be available. If once the thread block finishes, the shared memory will get deallocated automatically. Then you have constant memory. Constant memory and texture memory were particularly designed for processing GPU or graphics, basically. It is in the device memory. It is also cached and dedicated per SM constant cache. Constant memory is only read-only memory. Yeah, someone has raised his hand. Yes, Gautam, you have any doubts?
Yes, ma'am. So, ma'am, this shared memory across what is the zone it is shared? I mean, is it block level shared memory or something else? And across the block it is shared? Okay.
Shared memory is shared across a block only.
So
All the
multiple
threads
blocks
in
will
a
have
block.
access.
No, all threads in one block will have access.
Okay. So specific to one block shared memory.
Yes.
Okay.
Yeah, multiple
And ma'am,
blocks cannot share the memory.
this thread, is it a hardware thing or normally thread comes into the OS and software part, right? So how come block having the predefined thread initially?
Yes. See, a thread is a software concept in computing, right? It is like basically it is a separate flow of execution within, and within in terms of CPU, it's within a process. For GPU, it is So again, a software terminology or software concept, but the GPU threads are slightly lightweight and they are designed, to just execute instructions which are given to them.
Okay,
So,
perfect.
so GPUs threads are meant to only provide you high throughput and performance on the hardware codes that you have. So each SM will have, let's say, hundreds of codes. And when you launch these threads, they are supposed to do the execution of each of these codes at a time, whichever is available. So threads, in GPU's case, it's a basic execution unit which will run a sequence of instructions. A block will be a group of threads which can cooperate and share some memory. Is it clear?
Yes.
Moving on. Okay. So constant memory is read-only memory. So it performs best when all the threads in a war read from the same memory address. Single read from a constant memory can be broadcasted to all the threads in a war. But usually for general purpose GPU computing, we hardly use constant memory. Depends if you have any specific, but this is only read-only memory. You cannot update this memory. So there has to be some specific applications where you need them. Then you have texture memory, which will reside in your device and is cached in per. Again, it's read-only. Why particularly texture memory was designed was for graphics processing applications, where you know that for specifically for gaming applications, when you, let's say, enter a room, there is some texture on the wall, right? Or texture on the floor, which will get repeated multiple times. So such repeated textures are put in texture memory because it's optimized for this 2D spatial locality and fetched from this texture memory, because you can fetch it again and again and just replicate it wherever you want. That's why the texture memory was designed. Again, we do not make a lot of use of texture memory for general purpose GPU processing. If you need it specifically and know the exact utilization, you can go ahead. But as a programmer of general purpose GPU computing, you will mostly deal with shared memory and global memory. Register local memory will get utilized on its own, but we will not be doing anything special to ensure that how many, may not go to the minute detail of how the registers are allocated, how local memory is being used. What we might be concerned with is with whether we are using global memory, whether you want to use shared memory, and how do we optimize it. So how we allocate and deallocate memory is using these functions: CUDA, memcopy, host to host, host to device, device to host, and device to device. Right? This is how we get data from global memory, from your host memory to your global memory. So here you can see that your CPU is connected to your CPU memory, GPU is connected to your GPU memory. What do you think is the bottleneck in this image? It is the PCI transfer. PCI transfer is 8 GB per second. whereas global memory, GPU to global memory is 144 GB per second. So it takes significant amount of time to move any data from your CPU to your GPU. So this link between your CPU and GPU via this PCI bus is much slower compared to the amount you can transfer, the speed or bandwidth or the throughput you can get from the GPU memory to your GPU. But we may not be able to skip this every time, and we have to do this mandatorily. But we also have to keep track that this is going to affect the performance of your application as well. So how much data you transfer from your CPU to GPU also adds to the total execution of your code. So there is another, maybe let us take a break and maybe then we should, yeah, zero copy we should discuss later because it will be too much. So let us, it's 9:17. We can start around 9:25. Let's take 7-8 minutes break and come back. So, what we have something called a zero copy memory, which is a pin memory on our CPU. What is a pin memory? Is a memory which you assign on your CPU, which is not pageable. What do you mean by that? Is you cannot replace this memory, because what happens is when you're trying to move some data from your CPU to GPU, from your GPU's RAM, if it is not pinned and if it is still pageable, what will happen is, if the RAM requires that part of the memory for some other task it is doing, it might just replace it, right? So hence, you need this memory that you have on your CPU has to be non-pageable, that is page locked, and this memory of your CPU you can use directly from your CPU for any task done on your GPU or any code done on your GPU. So this kind of memory, zero copy memory, is helps you, or it allows the GPU to directly access host CPU memory without any explicit CUDA mem copy. You don't have to copy anything from your CPU to your GPU. You can directly use using zero copy memory. Now, when can you use this? It is useful when the data size is very small, or you want to access this once or only limited number of times, and PCI transfer is more overhead compared to just fetching the data from CPU. And in case, as we know, that GPU memory is very limited, right? You have fixed GPU RAM. It could be 2 GB, 4 GB, 8 GB, or like 80 GB maximum you can have. Whereas CPU memory, in most cases, will be much more than your GPU. In those scenarios also, you can use zero copy memory. So how it works is, you allocate first the pin host memory, and then get a device pointer for the same memory and use this data. So you first enable the host mapping, which is optional but recommended. Allocate a mapped pin memory on this by using CUDA host malloc alloc mapped. Then this data that you allocate is pinned. Then create a pointer for this and point this CUDA host get device pointer to the host device, and then send this pointer directly to your CUDA kernel, and then free this host memory that you have used. Let us see another example. I hope this code is visible. Here, we first created this pointer, then allocated this memory on device by using CUDA host alloc mapped. Then to this pointer, we assign some data on your CPU. Then create a device pointer to the same memory location. So first declare this pointer and then use the function CUDA host get device pointer, provided it's the pointer and what it should point to. This pointer then you send to your kernel. On your kernel, you will get this data and you will do the computation, whatever you want to do. And this computation will be done by your GPU directly on your host memory. and you are not doing this on your GPU memory using zero copy. Then the results can be printed and then you can free this host memory. Is the example clear? How we can directly work on the CPU host memory. Here host is our CPU, devices are GPU, by using a few functions. First, CUDA host alloc map, then create a device pointer, then send this device pointer to your kernel function. Kernel function will execute, do this, update this, and then those results you can print here. And you can free the host. You also have unified virtual addressing, which is introduced in CUDA 4.0. Here, with UVA, host memory and device memory feel like they share a single virtual address space. So here, without UVA, it looked like GPU's memory, CPU's memory, and so on. Now, you get a unified virtual memory space where you feel that GPUs are and CPU memory are uniform and they have the single virtual address space. So with this UVA, the memory space referenced by a pointer becomes transparent to the application code. The pin host memory allocated with CUDA host alloc has an identical host and device pointer, and we can then pass the return pointer directly to our kernel function. Then we also have unified memory, which was introduced in CUDA 6.0, where you can create a pool of managed memory where each allocation from this memory pool is accessible by both GPU and CPU using the same pointer. The underlying system will automatically migrate the data in this unified memory space, which is between host and device, and use a single pointer. With zero copy, we needed two pointers. With unified memory, which is you use a single pointer, but the concept is similar to zero copy. So how do you use unified memory? Host and device can use this single pointer data. You allocate this memory by calling CUDA malloc managed. You then create a kernel, send this data directly to this kernel, and then free this data. This was introduced in after 6.0 compute capability. Moving on, with respect to GPU global memory, and shared memory, there are performance scenarios where, based on the type of access to these two memory, global and shared memory, the performance of this memory will depend. That is, whether the amount of time taken to fetch data from global memory and write back to global memory will depend. So here, there are two types of accesses, which is one is aligned or coalesced and one is non-coalesced. So as you can see here in this figure, the coalesced memory access will be in a order, on a one. Uncoalesced will be in different order. Okay, that is irregular order. Now, why this affects the performance of your global memory is when you fetch data from your global memory, you fetch it in a line size, which is of 128 byte at a time. Okay. When you fetch 128 bytes at a time, if your one thread is accessing the first 16 bytes, or let's say if it's an integer, it will maybe access the first 4 bytes. The next thread, if may get since you're fetching 128 bytes, the next thread is already having the data, that the needed data is already fetched and it's available to it. So it can do it, use it immediately, and not wait again for the latency of around 800, 600 cycles to get the next data. But if the pattern of accessing this data is irregular, what might happen is the data is fetched, but it is not utilized because you need some other data and you go and fetch again. So you again go and fetch 128 bytes. So first access took 600 cycles, the next access also will take 600 cycles. And this will degrade the performance of your code. So how coalesced access will look like? It could be a vector addition where we consecutively access threads of consecutive memory locations. Okay. How uncoalesced will look is if we try to process metrics using column wise, because the way the data is stored in memory is row wise, and if we try to access this data from the memory column wise, it will give you irregular or uncoalesced access, and this affects the performance of your memory or performance of your application. So you should, when you're designing an application, try to use coalesced access as much as possible and avoid uncoalesced access, because uncoalesced access degrades your application's performance significantly. Coming back to shared memory, CUDA shared memory is one of the key components of your GPU. It is low latency, shared by all the threads in a thread block, which are currently executed on that asset. Hence, you can call this memory programmer managed cache. So why programmer managed cache is because programmer is supposed to assign this memory and then allocate this memory and utilize this memory. For example, before moving to example, shared memory, as we know, is very closer to SM than L2 and global memory. Its latency is roughly 20 to 30 times lower than global memory, at least 10 times lower. Bandwidth is nearly 10 times higher. It is available to all residence threads blocks on an SM. Since it is a critical resource, it might, if used a lot, might lead to reducing the number of blocks that you can assign to SM. You can declare this either local to our CUDA kernel, or you can also globally declare this. CUDA allows you to create 1D, 2D, and 3D shared memory arrays. 1D arrays can be dynamically declared. The user has full control over when data is moved into shared memory and when data is removed. CUDA makes it easier for the user to optimize the application because you have the fine-grained control. I'll show you how it is, and only then you will be able to appreciate. So how the global memory is available to you in CUDA is shared memory is available to you is shared memory is divided into 32 equally sized memory packets. So your shared memory that you have on your SM is divided into 32 equally sized memory banks. These memory banks are 32 because we have 32 threads in a warp. So if you, if a shared memory location is issued by a warp and does not access more than one memory location, it can be serviced by one memory transaction. So how, so because we have 32 banks in which the shared memory is divided into, one issue that can happen with shared memory is bank conflict. So bank conflict is where, if happens, the number of times, the amount of time it takes to access shared memory might get increased or will lead to poor performance. How that happens is when multiple addresses in a shared memory bank are being used or are being requested at the same time, what happens is the hardware will split this request into necessary number of conflict-free transactions. For example, if you see in this figure, the first figure, these are conflict-free accesses because you are accessing this. This is bank 0, bank 1, bank 2, bank 30, bank 31. You are accessing different, locations of the bank. So this is conflict-free. Even here, you are trying to access the same location, so that's fine. Even this is conflict-free access. But through shared memory, if you try to access two different locations, this becomes two-way conflict. If there are 3 places you are trying to access, then in the same bank, it becomes 3-way conflict. So what will happen in this case? Maybe this will be serviced first, and this request will have to wait and do it second. In this case, this might be the happening first, then second, and third. So the access will get serialized. It will be executed one after the other, and hence the performance that you get from shared memory might get degraded a bit. May not be as bad as global memory, but it will get affected. So how do you avoid shared memory bank conflicts? Is by using something known as the technique of padding. So since we have 32 threads and 32 banks and 32 threads in a war, we know that for consecutive access, the access might happen, uh, in a order. So what we can do is we can add one more extra column of memory locations. So with this, what happens is when you are trying to access the same data, the bank 0 will have 0 data first in bank 1, 2, 3, and 4. The padding will come in place of bank 0. Then it will, keep getting added in different banks. So when consecutive access is happening to these banks, someone accessing the bank 0 and bank 0 in different banks, the 0th location will access different banks. And this really helps the time taken for fetching this data from shared memory. So how the code looks like is this. When you are trying to use a shared memory array, you declare it using shared. And then declare the array shared 32. This is important that you declare your array as shared. So now your compiler knows that this you are using shared memory. Now this shared, you store some data and then do the update and then send this shared memory to your global memory output. Now, to avoid the potential bank conflict, you add a padding of 1. So this padding will avoid the bank conflict and will help you to get better performance. So let me see if there is, sorry. Okay. I will, maybe in the next evening class, I'll put some results on how much is the difference between, after adding and before adding the bank conflict. Now, how do you configure the amount of shared memory that you have on your GPU is by default, there will be some configuration. But if you want to have more shared memory, you can configure that well as well. So each SM will have 64 KB of on-chip memory. And this 64 KB is divided between shared memory and L1 cache. So CUDA will provide you two methods for this device configuration and kernel configuration. Here you have to mention what is the configuration, that is what is the cache config you want. So there are four options. The first one is default, no preference. The second one is you say prefer shared. In that case, 48 KB will be assigned for shared memory and 68 KB will be assigned for your L1 cache. Prefer L1. In that case, 48 KB will be L1 cache, 16 KB will be shared memory. Prefer equal. In that case, 32 KB by 32 KB will be your shared and L1 cache memory. Now, when should you prefer shared memory? When kernel uses more of shared memory. When should you prefer cache? When kernel uses more registers, because those will be spilled in the cache. Shared memory is accessed through 32 banks and L1 is also accessed by cache lines. That's the difference between them. That's why shared memory is called programmer controlled cache. Now, how do you synchronize? Since shared memory can be simultaneously accessed by multiple threads, you would like to avoid the inter-thread conflicts when same shared memory location is modified by multiple threads without synchronization. In that case, you use two approaches, barriers and memory fences. So CUDA opts a weakly ordered memory model, which means that it does not control who is, in which order the updates are happening to the memory, or okay, if some read is happening, then write should not happen. A lot of control is not put or is not, or these rules are not applied specifically for CUDA. There are different kinds of memory models. There are something known as strict memory models. There are something called as sequential memory models. But those memory models have strict rules on how the data should be accessed or updated on memory. But CUDA does not do that because it wants to apply aggressive compiler optimizations. It wants to provide you the maximum performance that you want, and putting a lot of rules again may delay the execution, may delay the data fetching, or may delay the data updation. Hence, it is very important. At the same time, it is very important to use synchronization whenever necessary. At the same time, you should always weigh in whether you really need to synchronize. The reason why I'm saying this is, if you synchronize, all the threads will have to wait at that synchronization point till everyone completes. This degrades the performance. At the same time, if you do not synchronize, what might happen is, because you have not synchronized, you will end up not the threads might work on the way they want and might end up corrupting the results that we expect. So one method of using this barrier or synchronization is using void sync thread. So this sync thread function, what happens is it acts like a barrier in which where all the threads in a block will wait till everyone finishes and reaches that point. So when you have these global and shared memory accesses made by these threads, prior to this barrier point, if you expect them to be visible to all the threads, then you have to use the barriers. Or, if you don't want to corrupt the data, if you do not want to incorrect results, you might have to use the synchronization thread depending on the problem. So then you also have an option of memory fencing. These fences will ensure that any memory written before and after the fence is visible to the thread after the fence. Okay, whatever changes are done before the fence will be visible to after the fence. So there are three types of fences which are available to you. One is thread fence block, which ensures that all writes to shared or global memory by the calling thread before fence are visible to all the other threads in the same block after the fence. You also have a thread fence, which calls the calling thread until all of its writes to global memory are visible to all the threads in the same grid. Then you have thread fence system, which stalls the calling thread to ensure that all its writes to global memory, page locked host memory, and the memory of other devices are visible to all the threads in all devices and host threads. So this is how you can put a fence and ensure that the data is consistent across different types of memories depending on which kind of a fence you utilize. So this is an example of matrix multiplication, which is coalesced and uncoalesced. So here the data is coalesced because we are doing the fetching row wise, which is here row is block id x dot y, block dim dot y, and thread id x dot y. If the row becomes block id x dot x and block dim dot x and thread dot x dot x, this is misalignment and which will give you uncoalesced accesses. The same problem of matrix multiplication for coalesced and uncoalesced can be made faster if you use shared memory and or with the execution time can be better using shared memory because you're not fetching the data every time from the global memory. In that case, what you can do for matrix multiplication using shared memory is you can create this tiles of, yes, someone is saying something. So you can create these sub-matrices of your main matrix, that is A and B. You can copy these sub-matrices and store them in shared memory by A sub and B sub. And then you do the addition, matrix multiplication on A sub and using B sub. Here, get the data. Here is how you're multiplying A sub and B sub. This sum, so you get the data, you synchronize your whatever you fetched, then calculate the sum for all the 16 cross 16 block of matrix, then synchronize again and write this data to your global memory of C. So where you are using the global memory here is only when you're fetching data you fetch and store. The computation is done locally using the shared memory A sub and B sub, which are sub-matrices of your global memory. So this is how you can use global memory and shared memory in your code. And with the use of shared memory, because of the low latency, that is at least 10 times, in most cases 20 to 30 times lower than your global memory, you can get a better performance. Now, how do you avoid can this lead to bank conflict? There is a possibility that this can lead to bank conflict because it's 16 by 16 and we have 32 banks. So there is a possibility that when we are doing the computation, multiple threads might, access data from the same bank. So hence, how do we avoid bank conflict? Is we can do the padding in this case. And how do you do the padding? It just increase one element. In this case, you are increasing the element in the column wise, and this will ensure that you are adding the padding. All the computations remain same. You fetch the data from your global memory. For A, store it in your submatrix. Similarly, for fetch the data from global memory and store it in your submatrix, which is shared memory. Then you do the computation on your shared memory submatrices and store it, synchronize. Then add this shared memory results to your global memory. Move this shared memory results to your global memory. Here the sum is a local variable. Okay. So for each C, you get this sum from here. Is this clear? The performance comparison of padding bank conflicts, I'll add that in the evening slides, and I'll share how the coalesced and uncoalesced and padding, unpadding, or bank conflict affect the performance of your CUDA applications. Any doubt in terms of the memory model of CUDA we've discussed so far? I know it's a lot to process, and CUDA memory model is quite complex, but it is designed for the better performance of your applications on GPU, and it is designed in such a way that it tends to, caters to all the memory requirements of your application.
Ma'am, a quick wrap can you give on the banking, conflict, and padding?
Sure. Yeah. So, okay, as I mentioned, shared memory is divided into 32 banks. And why it is divided into 32 banks is because it is, it is divided into 32 equally sized banks. It's because we have 32 warps, which are 32 threads in a warp. So when a CUDA kernel executes on a GPU, it is divided into a set of 32 threads, which is called a warp, for which we assign the instructions. And that's why shared memory is also designed in such a way that it is divided into 32 banks. Now, these 32 banks can be accessed by your threads, and when they are being accessed, if the access happens to, like, parallelly access is happening to different banks, then that means there is no conflict. These accesses can happen simultaneously in the same cycle. But what if we have such accesses where there are accesses that are happening to the same bank, that you are trying to fetch data from the same bank in the same cycle? Now, if there are two read accesses in the same bank, obviously you cannot cater to both the accesses at the same time. You might have to do one thing first and then followed by the next thing. In that case, this might happen first and this might be the second access. In such a scenario, you have to do this access second time. So what might happen is, here, if first access is taking 30 cycles, the second access, because the second access will take 30 plus 30, so it will take around 60 odd cycles, right, for fetching the data, same data. So this degrades the performance when there is bank conflict. Imagine that, 5 threads are trying to access the same bank at the same time. So 5 threads means 5 into 30. So approximately 150 cycles. So this is a larger delay. So this way, you should try to avoid these bank conflicts that are happening in your code. Okay. And the way you can avoid this is using padding. So when you create a shared memory, matrix, that time, if you add one extra column to this matrix or to this array, in that case, what happens is, when this extra array that you are adding, when it is assigned to your bank, that time you replace the, let's say in this case, if this is the 0th element of your array, this extra one will get assigned to the same bank where 0th element is being used. So, for example, in your code, if 2 threads are accessing the bank, the 0th element, okay, the first 0th element and the second 0th element, in that case, they can easily access this without any conflict, because this extra element, which does not have any data, has taken the space of in the same bank as the bank 0. And because of this, you shift, the access gets shifted and there is no conflict here. In terms of code, this looks like the same code, just adding one extra, column and row, you shift your accesses.
Ma'am, in
Yes.
in open book test, so will there be direct questions as well, like why there are like 32 threads, or kind of like that?
Yes. So your open book will be in the center. I'm just asking you that.
Yeah.
So you'll be going to a center with the printouts of your slides.
Yeah.
Is that the
Right.
case?
Yes.
Okay. Okay. In that case, I will try to have some direct questions as well.
Okay. And are the reference books also allowed, or only the slides?
What are the instructions that you have received?
I'll have to go through them because I think the thing clear is about the lecture slides.
Okay.
We have
Even
not heard
what we are
about the.
told is we have to give you lecture slides to be printed.
Yeah, yeah.
So yeah, so my understanding is it will be lecture slides.
Okay.
Ma'am, we have to take all the printout of all the slides. It's too huge.
That's up to you. If you think they'll be useful, then you will have to print. I don't think there is any compulsion from the team side, but if you need them, you'll have to get them printed. I'll try to see if I can ask some direct questions as well, because anyways you'll be answering in. If you'll be answering in a center, then I can ask some direct questions. That would be an issue. But there will be some programming questions as well, because we have done CUDA. So there might be some direct questions on the Hadoop side. There we can explore some direct questions.
Ma'am, hello.
Yes.
Can you share the important question banks for that?
Okay, let me see if I can do that.
Okay, thank you, ma'am.
Ma'am, and if the lab credentials get exhausted, is there a way we can ask them again to reset it?
What?
If the labs get used fully.
Lab. Yes, you can send a mail and then they do. They've done
Okay,
it. The student in the past. Yes.
Is there any reference mail we have?
I think there is bits lab beta. Let me check.
Hi ma'am. So in exam, right? So what are the content will be asked? Like, is it asked from first session to 16th sessions, or
Okay. I can what? How do you want to? Wait. What is the weightage this time?
40%? I guess.
I think 40 marks.
Yeah.
Okay, 40%.
And yeah, it is given, I think, syllabus, I think 1 to 16.
Okay, the whole thing is asked. Okay. Fine. I can ask on the whole thing, but considering the quotes, maybe an answer to also. I'll ask questions on maybe OpenMP and CUDA only for the Compre and whatever covered after midsem. I'll not ask on MPI and P-threads. It will be too much for you all to study. Is that fine?
Yeah. So open MP and
Whatever was covered after midsem.
okay.
Yeah, I think that's really helps us.
Yeah.
Yeah,
I
ma'am.
think
Thank
it would
you.
be too much for.
Yeah. And this time I think semester's time also less, right? In 4 months we
Yeah,
are
yeah.
covering.
Somehow this felt all rushed. I agree.
Yes, ma'am.
So maybe I'll only ask a few questions on OpenMP and whatever was covered after midsem.
Ma'am, normal time, I mean, it is 6 months, right? Semester's timing, I mean,
Yeah,
span of
this time I don't know why it got delayed.
yeah, because we started from August, July last first class, I mean, orientation started. I'm a 27.
Yeah, usually it starts July 1st or second week. It starts.
And by the moment 4 months we are final semester giving.
Yeah, I understand. Yes, it's a lot.
Even after mid-sem, it's a very less time. to
Yeah,
study.
it is. It is now. It's like almost the course is ending. Yeah, it feels strange. I agree.
It's just like we just finished with the midterms, and
I
now
know.
we are going to be ready for a comprehensive.
I I know, I know, I know.
Your
I,
voice is low.
yeah, I know. I agree.
What
I
I'm
agree.
uh, what I'm saying, we just finished with the midterms, and it's looks like now like we just finished the midterm, and now we are preparing for the comprehensive.
Yes, yes. It felt like so. This happened.
Yeah,
This
it's so
semester felt
quick.
very rushed. I completely agree. Yeah, hopefully the next semester will not be like that. We will space it well. Okay, then I'll announce it on Conta as well. I'll only ask questions on OpenMP and whatever was covered after midsem. Okay.
Okay,
Yeah,
ma'am.
man.
Let's
And
see if I
ma'am,
can.
for I think two quizzes already happened, right? So anything else
Yeah, third
coming?
one is
No, right?
third one is also up, right? You've
It's a
not seen it?
it's a yeah, it's a three quiz. It's all third three quizzes, Gautam. You can
Okay,
check
Yeah,
okay.
Yeah,
it.
third,
third
third
one
quiz
is
also
up. Please
announced.
answer. Please answer it. I think 11th is the last day or something.
Okay, okay. Let
Yes.
me check
I've
the
already
link.
given one extra day this time so that one is
Thank you,
left
ma'am.
out.
Yeah.
Okay.
So this quiz, I mean, after midsum we'll cover, right? Mostly the syllabus. Third
Yes,
one.
yes. I know. I know.
Okay.
Uh,
Okay.
it is, yeah, whatever after midsem before today's class. So I also had a very little content to ask from. So, but
Yeah.
yes,
Okay.
we have to time it as per the course and yeah. So,
Ma'am, the practice problem has assignment.
Hmm.
So that will be under practice only, right? That assignment will be.
no evaluation of any assignments. Only quizzes
Okay.
and yeah,
Yeah.
midsem and
Because
comp.
yeah, it is mentioned three quizzes or two assignments. I think we are going with
Yeah.
quizzes. Yeah.
Quizzes
That's
only
helpful.
I do uh, because of availability of lab was pretty, it was pretty late by the time we got the lab access and
Yes,
we
ma'am.
all hardly got scope to practice and so I felt assignments will not be fair and you all may or may not have the resource required for trying out the things like you might be using some other computing system you might not be well versed with C so considering all these things I decided to opt for only quizzes. Okay, so fine. I have very few things that I need to cover regarding CUDA in terms of that is in terms of how we profile CUDA applications and also a bit on how we can optimize our problems programs which will help the compiler to optimize our code better. So we'll see some interesting compiler optimizations in the evening class today. Okay. Fine then. See you in the evening. Any
Okay,
other
thank you, ma'am.
doubts or queries?
Ma'am, hello.
Yes, yes.
Yeah, the difficulty level in the exam for the AC3 in regular and makeup will be same or it will be different? How it is?
Yeah, I'll try to keep it same. Well, I'll try
Yeah,
my
ma'am.
best to have it same. Yes.
Okay, ma'am. Thank you.
And ma'am, I assume like in a exam, right? So maximum question will be asked from the programming, isn't it?
Yes, because it is introduction to parallel and distributed programming. I cannot skip programming from the question paper. So at least a few will be there on programming.
Okay.
Ma'am, but out of 40% weightages, so how it will be coding part? It is 50/50 or how it is?
Mm, yeah, assume it to be at least 50-50. At least.
Okay, ma'am. Thank you.
Okay, then I'll see you all in the evening and we'll continue our discussion on CUDA.
Thanks, ma'am.
Thank you.
Thank you.
Thank you, ma'am.
Thank you, ma'am. Thank you.